Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on atomic and nuclear phenomena. Let's go ahead and get started with problem number 1. Problem number 1 says, if the work function of a metal is 6.622 times 10 to the minus 20 joules, and a rate of electromagnetic radiation with a frequency of 1 times 10 to the 14 hertz is incident on the metal, what will be the speed of the electrons ejected from the metal? And here we're given Planck's constant, and we're given the mass of the electrons. To solve this problem, we're going to first calculate the kinetic energy of the ejected electrons, and then from there we can use the kinetic energy to find the speed of the electrons. Now, how are we going to do that first part? To calculate the kinetic energy of the ejected electrons, we're going to be using this equation right here. This equation says that the kinetic energy of the ejected electrons is equal to Planck's constant multiplied by the frequency of the incident light minus the work function of the metal. Now we're given all three of these variables, so we can go ahead and just plug them in. Planck's constant multiplied by the frequency of the incident light minus the work function. Now we can simplify this multiplication term right here by simply multiplying 6.626 by 1. That gives us 6.626, and then multiplying 10 to the negative 34 by 10 to the 14. This is just going to be a sum of the exponents, and that gets us 10 to the minus 20 power. Now from here, we're going to subtract our work function, 6.622 times 10 to the minus 20. Now notice, both of these terms have a 10 to the minus 20, so we can go ahead and take that out and just have in parentheses the difference between 6.626 and 6.622. This gets us a difference of 0.004, and that's multiplied by 10 to the minus 20. From here, we can move the decimal place 3 units to the right. When we do that, we have to subtract minus 3 from the exponent, and that gives us the kinetic energy of the ejected electrons. It is equal to 4 times 10 to the minus 23 joules. From here, we can use the kinetic energy to find the speed of the electrons. We know that kinetic energy is equal to 1/2 mv squared. We're ultimately solving for this v term, so we can rearrange the equation. When we do that, we get that v is equal to the square root of 2k divided by m. K is the kinetic energy we just calculated. M is the mass of the electron. Now we have all of these variables as well, so we can go ahead and plug them in. We have the square root of 2 multiplied by 4 times 10 to the minus 23 joules, and this is divided by 9.1 times 10 to the minus 31. 2 times 4 here is equal to 8, so we have 8 times 10 to the minus 23 divided by 9 times 10 to the minus 31. I'm going to approximate this 8 as a 9. So now we have 9 divided by 9. That gets us 1. And then we have 10 to the minus 23 divided by 10 to the minus 31. This is going to simply be 10 to the minus 23 minus negative 31. And that gets us 10 to the 8. So now we just need to take the square root of 1 times 10 to the 8, and this gives us 10 to the 4 meters per second for the speed of the electrons. Looking back at our answers, the answer choice that's closest to this value is C, 9.38 times 10 to the 3 meters per second. Now it might not look exactly like this, but we can rewrite this as 10 times 10 to the 3, which is rewritten as 1 times 10 to the 4, which is close to what we got here with our approximations. So once again, The correct answer for problem 1 is C. And now we can move into problem 2. Problem 2 says, what is the wavelength of a photon that causes an electron to be emitted from a metal with a kinetic energy of 50 joules? Note that the work function of the metal is 16 joules, and we're given Planck's constant. To determine the wavelength of the light ray, we first have to calculate its frequency from the photoelectric effect equation. This equation says that the kinetic energy of the ejected electron is equal to Planck's constant multiplied by frequency minus the work function of the metal. We ultimately want to solve for F, so we're going to rewrite this equation to solve for frequency. Frequency is equal to the kinetic energy of the ejected electron plus the work function of the metal divided by Planck's constant. We have all of these variables, so let's go ahead and plug them into our equation. This gets us 50 joules plus 16 joules divided by 6.626 times 10 to the minus 34 joules times second. Now in the numerator, 50 plus 16 gets us 66, but we're going to write it in scientific notation so it matches our denominator, and it's going to make the division a lot easier. So we can rewrite 66 as 6.6 times 10 to the power 1. And then we're going to approximate our denominator here, our Planck's constant, from 6.626 to just 6.6 times 10 to the minus 34. This makes it really easy because now we have 6.6 divided by 6.6, which is equal to 1. And then we have 10 to the power 1 divided by 10 to the minus 34, and that gets us 10 to the 35, 1 over second for our units, which is equal to hertz. From here, we can take this frequency and determine the wavelength. To do that, we're going to use this equation, which states that the speed of light, c, is equal to the frequency of light multiplied by the wavelength of light. We want to solve for wavelength, so we're going to rearrange this equation, and that gets us that the wavelength is equal to the speed of light divided by frequency. This is going to be equal to approximately 3 times 10 to the 8 meters per second, divided by 10 to the 35 hertz. We essentially have here 3 divided by 1, which gets us 3, and 10 to the 8 divided by 10 to the 35, which gets us 10 to the minus 27. Hertz is just 1 over second, so those cancel out in the numerator and denominator, and we're left with units of meter. So our wavelength is equal to 3 times 10 to the minus 27 meters, and this best matches answer choice B. So the correct answer for problem 2 is B. Let's do problem 3 next. Problem 3 says, which of the following statements is inconsistent with the Bohr model of the atom? As a friendly reminder, the Bohr model of the atom describes electrons as existing in stable discrete energy levels or orbits around the nucleus. Some key points that we've discussed is 1, electrons can transition between energy levels by absorbing or emitting a photon. Second, the energy of the absorbed or emitted photon must exactly match the energy difference between the two energy levels. And 3, electrons in higher energy levels can emit a photon to drop to a lower energy level, while electrons in lower energy levels can absorb a photon to jump to a higher energy level. Keeping that in mind, let's work through each of our answer choices. A says energy levels of the electron are stable and discrete. This is consistent with the Bohr model. Energy levels are quantized, meaning electrons can only occupy certain stable orbits with specific energies. This stability is one of the core ideas of the Bohr model. So this is true. We're looking for something that's inconsistent with the Bohr model. Let's try answer choice B. Answer choice B says An electron emits or absorbs radiation only when making a transition from one energy level to another. This is also consistent with the Bohr model. Electrons only interact with electromagnetic radiation when transitioning between energy levels, either absorbing a photon to move to a higher energy level or emitting a photon to move to a lower one. So B is also consistent with the Bohr model. Let's try answer choice C. This says to jump from a lower energy to a higher energy orbit, an electron must absorb a photon of precisely the right frequency such that the photon's energy equals the energy difference between the two orbits. This is also consistent with the Bohr model. The energy of the photon must exactly match the energy gap between the two orbits. That's calculated using E equals hf. So C is also consistent with Bohr's model. D says to jump from a higher energy to a lower energy orbit, an electron absorbs a photon of a frequency such that the photon's energy is exactly the energy difference between the two orbits. Now, this is inconsistent with the Bohr model. Electrons moving from a higher energy to a lower energy level do not absorb photons. Instead, they emit photons. The energy of the emitted photon corresponds to the energy difference between the two levels. Absorption, please remember, only occurs when electrons move to a higher energy level. So we're looking for the statement that's inconsistent with the Bohr model of the atom. That's going to be answer choice D. So the correct answer for 3 is D. Beautiful. Next up, we have problem 4. Problem 4 says, when a hydrogen atom has an electron that falls to the ground state from the n equals 2 state, 10.2 electron volts of energy is emitted. What is the wavelength of this radiation? Here we're told 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And once again, we're given Planck's constant. To solve this problem, we're going to take advantage of 2 important equations. The first one is the energy of the photon is equal to Planck's constant multiplied by frequency. And the second equation is that frequency is equal to the speed of light divided by wavelength. I'm going to replace the frequency term in this equation with c divided by lambda. And this tells us that the energy of the photon is equal to Planck's constant multiplied by the speed of light divided by wavelength. This equation is really important because we're given the energy, we're given Planck's constant, we know the speed of light, and ultimately we want to solve for lambda. We want to solve for the wavelength. So we can rearrange this equation to solve for lambda. Lambda is equal to Planck's constant multiplied by the speed of light divided by the energy of the photon. Now you might get really excited because we have all of these variables and you might quickly plug them in, but there's one thing that we need to be really careful about, and that is the units for the energy term. We're told that 10.2 electron volts of energy is emitted. In order for the units to cancel out appropriately in this equation, and for us to calculate wavelength in units of meters, we need energy to be in units of joules. So we need to convert electron volts to joules. Now, thankfully, we are given that conversion. So let's go ahead and do that, and then we can plug things into our equation and solve for wavelength. Now, we have 10.2 electron volts, and the conversion is that for 1 electron volt, we have 1.6 times 10 to the minus 19 joules. We're going to approximate this to 10, and that gets us 1.6 times 10 to the minus 18 joules. Now we can go ahead and plug things into our equation. Planck's constant is 6.626 times 10 to the minus 34 joules times second. Speed of light is approximately 3 times 10 to the 8 meters per second. And that is going to be divided by the energy of the photon, which we just calculated to be 1.6 times 10 to the minus 18 joules. Now I'm going to approximate this value to 8. I'm going to approximate this value to 2, and I'm going to keep this as 3. We have 8 times 3 is 24, divided by 2 is equal to 12. So now that we got these numbers out of the way, we can focus on these terms. In the numerator, to deal with these terms, we just have to add the exponents together. So we have 10 minus 34 plus 8, and that gets us 10 minus 26. And then in the denominator, we have 10 to the minus 18. Now to deal with this division, we're going to be subtracting the exponents. So 10 to the minus 26 minus negative 18. And this gets us 10 to the negative 8. So our answer here is 12 multiplied by 10 to the negative 8 meters. We can alternatively write this as 1.2 times 10 to the minus 7 meters. And this matches answer choice B very closely. So the correct answer for problem 4 is B. Let's move on to problem 5. Problem 5 says the figure below illustrates an electron with initial energy of minus 10 electron volts moving from point A to point B. What change accompanies the movement of the electron? So in this problem, an electron is transitioning from point A, which is further from the nucleus, to point B, which is closer to the nucleus. The electron is essentially moving from a higher energy level to a lower energy level. When an electron transitions to a lower energy level, the difference in energy between the two levels is released. This energy is emitted as a photon of electromagnetic radiation. The emitted photon's energy corresponds exactly to the difference in energy between the initial and final levels. So therefore, as the electron moves from point A, which is a higher energy level, to point B, which is a lower energy level, a photon is emitted. And that means that the correct answer for problem 5 is answer choice B. Next up, we have problem 6. Problem 6 asks, which of the following 4 fundamental forces is primarily responsible for holding the nucleons together? The nucleus of an atom consists of protons and neutrons, collectively called nucleons. Protons are positively charged, so they naturally repel one another due to the electrostatic force, which acts between charges of the same sign. However, despite this repulsion, nucleons are tightly packed within the nucleus. This observation indicates the presence of a stronger force that can overcome the electrostatic repulsion. This force is known as the strong nuclear force, which is the fundamental interaction responsible for binding nucleons together. The correct answer for problem 6 is B. The strong nuclear force is the attractive force that holds protons and neutrons together in the nucleus. Beautiful. Problem 7 says, all of the following statements about the photoelectric effect are true, except blank. Let's go through each of the answer choices and figure out which one of these 4 statements is incorrect. Answer choice A says that the intensity of the light beam does not affect the photocurrent. This statement is false, and it actually makes it the correct answer for this problem. But let's explain. The intensity of the light beam is directly proportional to the number of photons striking the material per unit time. If the frequency of the photons is above the threshold frequency, a higher intensity light beam will result in more photons, which means we're going to eject more electrons and thereby increase the photocurrent. Therefore, intensity directly affects the photocurrent. Let's still work through answer choices B, C, and D. B says the kinetic energies of the emitted electrons do not depend on the light intensity. This statement is true. The kinetic energy of the emitted electrons is determined solely by the energy of individual photons, and those depend on the frequency of the light and not on the intensity. The relationship is given by the following equation. K, the kinetic energy, is equal to HF minus W, where HF is the photon energy and W is the work function of the material. Increasing the intensity only increases the number of photons, not their energy. So that means that the kinetic energy of the ejected electrons remains unaffected by intensity. Statement B is a true statement. Answer choice C says a weak beam of light of frequency greater than the threshold frequency yields more current than an intense beam of light of frequency lower than the threshold frequency. This statement is also true. For electrons to be ejected, the frequency of the light must be greater than the threshold frequency, regardless of the light's intensity. If the frequency is below the threshold, then no electrons are ejected, regardless how intense the beam is. A weak beam of light with a frequency above the threshold that can eject some electrons, that's going to produce a current, while an intense beam of subthreshold light cannot eject any electrons, resulting in no current. Now, what about answer choice D? Answer choice D says, for light of a given frequency, the kinetic energy of emitted electrons increases as the value of the work function decreases. This statement is also true. The kinetic energy of the emitted electrons is inversely related to the work function of the material. And again, we can look at this equation to figure that out. For a given frequency f, a smaller work function leaves more excess energy for the electrons, resulting in a higher kinetic energy. So this relationship aligns with the principles of the photoelectric effect. So again, to summarize, statements B, C, and D are all true, but statement A is false, so the correct answer for problem 7 is A. Let's do problem 8 next. Problem 8 says, what is the binding energy of the argon-40 isotope in mega-electron volts? Note that the mass of a proton is 1.0073 atomic mass units. The mass of a neutron is 1.0087 atomic mass units. And the mass of the argon-40 nucleus is equal to 39.9132 atomic mass units. And then the last thing we're given is that C squared is equal to 932 mega-electron volts per atomic mass unit. To determine the binding energy, we must first determine the mass defect. The mass defect is simply the masses of each of the protons and neutrons in the unbound state added together minus the mass of the formed argon-40 nucleus. Now, the argon-40 nucleus contains 18 protons and 22 neutrons. So this term, the mass of the free nucleons, is going to be equal to 18 multiplied by the mass of the proton plus 22 multiplied by the mass of the neutron. That gets us the mass of the free nucleons, and then we subtract the mass of the formed argon-40 nucleus, which we're given to be equal to 39.9132 atomic mass units. The mass defect, once we calculate this, is equal to 0.4096 atomic mass units. Now that we know the mass defect, the binding energy can be determined using Einstein's famous equation E equals mc squared. M is going to be the mass defect here, which is equal to 0.4096 atomic mass units. C squared is equal to 932 mega electron volts per atomic mass unit. So atomic mass units cancel out here. We're going to multiply these out. We're going to approximate this to 0.4, and then we're going to approximate this to 900, and this gives us 360 mega electron volts. And that means that the correct answer for this problem is going to be C, because that value is the closest to 360 mega electron volts. Let's do problem 9. Problem 9 says, which of the following correctly identifies the following process? We notice that in the initial state, the gallium nucleus interacts with an electron from its surroundings, and this reaction results in the production of zinc. Now let's look at the atomic number for gallium and zinc. The atomic number for gallium is 31, indicating it has 31 protons. After the reaction, the resulting zinc nucleus has an atomic number of 30, meaning that one of gallium's protons has been converted into a neutron. Looking at the mass number, it's the same. So the mass number remains unchanged at 67 because no protons or neutrons are added or removed from the nucleus. The reaction just involves the transformation of a proton into a neutron, which does not alter the total number of nucleons. Also, we make note that the electron in this reaction is absorbed by the nucleus, and this distinguishes the process as one involving the interaction of an orbital electron with a proton in the nucleus. Taking that all together, we can confidently say that this process depicted here is known as electron capture. And during electron capture, an inner shell electron is absorbed by the nucleus. The electron combines with a proton to form a neutron, and that reduces the atomic number by 1 while leaving the mass number unchanged. And the resulting element is 1 atomic number lower than the original. So the correct answer for problem 9 is C. Let's take a look at problem 10. Problem 10 says, consider the following fission reaction. The masses of the species involved are given in atomic mass units below each species, and 1 atomic mass unit can create 932 mega electron volts of energy. What is the energy liberated due to the transformation of mass into energy during this reaction? Let's break this problem down. This problem presents a reaction and asks for the energy liberated due to the transformation of mass into energy. To convert mass into energy, we're told that 1 atomic mass unit can be converted into 932 mega electron volts of energy. All we need to do now is calculate how much mass in atomic mass units is converted in the reaction. We're going to calculate the mass defect, and we're going to do that by summing up the mass of the reactants, by summing up the mass of the products and then taking the difference. When we take the difference, we get a mass defect of 0.003 atomic mass units. To obtain energy from mass, we simply have to multiply by the conversion factor. So the energy here is going to be equal to 0.003 multiplied by 932. This is approximately 0.003 multiplied by 900, and this gives us 2.7 mega electron volts. This value is really close to answer choice C, so the correct answer for problem 10 is C. Problem 11 says, element X is radioactive and decays via alpha decay with a half-life of 4 days. If 12.5% of an original sample of element X remains after n days, what is the value of n? Because the half-life of element X is 4 days, 50% of the original sample is going to remain after 4 days. After 8 days, only 25% of the original sample will remain. And then after 12 days, we're going to have 12.5% of the original sample remaining. Therefore, n is equal to 12, and the correct answer for problem 11 is C. Problem 12 says a graph of an exponential decay process is created. The y-axis is the natural logarithm of the ratio of the number of intact nuclei at a given time to the number of intact nuclei at time t equals 0. The x-axis is time. What does the slope of such a graph represent? To start solving this problem, we're going to write the radioactive decay equation. This equation says that n is equal to n naught e raised to the negative lambda t. N is the number of intact nuclei at time t. N naught is the initial number of nuclei, so the number of nuclei when t equals 0. Lambda is the decay constant, and t is time. So this equation describes how the number of nuclei decreases exponentially over time. Now, the graph that's described in this problem, it plots the natural logarithm of the ratio of n to n naught. To obtain this expression, we're going to have to take the natural logarithm of both sides of the exponential decay equation. When we do that, we get natural log of n is equal to natural log of n naught plus the natural log of e raised to lambda t. Now, using the log property that says that natural log of e raised to x is equal to x, we can go ahead and rewrite this term as just negative lambda t. So now our equation reads that the natural logarithm of n is equal to the natural logarithm of n naught minus lambda t. The next thing we're going to do is we're going to subtract natural log of n naught from both sides. This gets us that the natural log of n minus the natural log of n naught is equal to negative lambda t. This here can be rewritten as natural log of n divided by n naught, and that is equal to negative lambda t. Now this is the equation of a straight line in the form of y equals mx plus b. Y is the natural log of n divided by n naught. X is equal to t. The slope is negative lambda, and the y-intercept is 0, because when t equals 0, then the natural log of n divided by n naught is also equal to 0. So from the equation, the slope of the graph is clearly negative lambda, which means that the correct answer for problem 12 is B. Now we can move on to problem 13. Problem 13 says a certain carbon nucleus dissociates completely into alpha particles. How many particles are formed? A typical carbon nucleus contains 6 protons and 6 neutrons. An alpha particle contains 2 protons and 2 neutrons. Therefore, one carbon nucleus can dissociate into 6 divided by 2 alpha particles. 6 divided by 2 is equal to 3, so we can say that one carbon nucleus can dissociate into 3 alpha particles. That means that the correct answer for problem 13 is C. Problem 14 says, the half-life of a carbon-14 is approximately 5,730 years, while the half-life of carbon-12 is essentially infinite. If the ratio of carbon-14 to carbon-12 in a certain sample is 25% less than the normal ratio in nature, how old is the sample? We're told that the half-life of carbon-14 is approximately 5,730 years, while carbon-12 has an effectively infinite half-life. When the ratio of carbon-14 to carbon-12 in a sample is 25% less than the natural ratio, then this indicates that less than one half-life has passed. During one half-life, the amount of carbon-14 would decrease to 50% of the original value. Since the sample still retains more than 50%, it has to be less than 5,730 years old, which means that the correct answer for problem 14 is answer choice A. And with that, we can move into our last and final problem. Problem 15 says, a nuclide undergoes 2 alpha decays, 2 positron decays, and 2 gamma decays. What is the difference between the atomic number of the parent nuclide and the atomic number of the daughter nuclide? Now, an alpha decay reduces the atomic number by 2 because the nucleus loses 2 protons. Since there are 2 alpha decays, this results in a total reduction of 4 in the atomic number. Next, we have a positron decay. This reduces the atomic number by 1 because a proton is converted to a neutron. So again, it reduces the atomic number by 1. With 2 positron decays, the total reduction is 2. Finally, we have gamma decay. This involves the emission of energy, but it doesn't change the atomic number. So even though there are 2 gamma decays, their net effect on the atomic number is 0. Again, because gamma decay just involves the emission of energy. Now adding up all of these changes, we have 4 plus 2 plus 0. This gives us a total reduction in the atomic number that's equal to 6. Therefore, the difference between the atomic numbers of the parent and daughter nuclide is 6. So the correct answer for problem 15 is D. And with that, we've completed our practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.